Hi guys, in the last lecture we first of all saw equivalent circuit of the induction motor. In this we saw stator side circuit which worked as the primary and rotor side circuit, and then we referred the rotor side parameters or rotor side electrical components to the stator side or the primary side. The transformation ratio that we used was n1 dash by n2 dash whole square, where n1 dash was n1 into kW1 winding factor of stator winding, n2 dash was n2 into kW2 winding factor of the rotor winding. And then we saw torque slip characteristic. Torque was given by m by omega s ve square by re plus r2 dash by s whole square xe plus x2 dash whole square into r2 dash by s. And when we neglected the stator impedance, it was m by omega s v1 square by r2 dash by s whole square plus x2 dash square into r2 dash by s. So this is what we saw in the last lecture. In this lecture, we will cover more about the torque slip characteristics and try to determine different torques, that is the maximum torque, starting torque. So let us proceed with the approximate analysis. So the approximate torque expression is given by, for 3-phase, 3 by omega s v1 square r2 dash by s plus x2 dash square into r2 dash by s. Now let us consider the case when slip is low. Okay, it will be slip is low. That means motor is under running condition. When motor is running at full load or at no load, then the speed is closer to the synchronous speed and thus the slip is low. So in that case, r2 dash by s is much greater than x2 dash. So this torque would become 3 by omega s v1 square into r2 dash by s divided by r2 dash by s whole square. So it will be s v1 square by r2 dash into 3 by omega s. So torque is directly proportional to slip. So under running condition we have linear torque slip characteristics. Torque is coming directly proportional to the slip. It is called as linear torque slip characteristic. So most of the time the torque slip characteristic will be linear, as the motor will be operated between no load and the full load condition. And no load speed is always greater than full load speed. So both will be lying in the linear region. Next, consider the other case when slip is high. Slip is high means NR is low. That means the starting characteristics. When the motor is just starting, the speed will be low, so slip will be high. In that case, R2 dash by S is much less than X2 dash. So torque will be 3 by omega S V1 square into R2 dash by S divided by X2 dash square. So here torque is inversely proportional to slip. Okay. So if torque is inversely proportional to slip, that means the torque will decrease with increasing slip, or the torque will increase with decreasing slip. So as slip reduces, torque increases, or we can say slip reduces means speed increases, the torque will also increase. Okay. So as the motor starts, the speed builds up and the torque of the motor will also keep on increasing. Okay. With the building speed, the torque will also increase. So if we talk about the rotor power factor, so this is about the torque. In low slip region, it is directly proportional to slip. In high slip region, it is inversely proportional to slip. So the rotor circuit was something like this. So rotor power factor would be R2 dash by S, that is R upon Z. Z will be R2 dash by S whole square plus X2 dash square. Again, when slip is low, R2 dash by S will be much greater than X2 dash, so we can neglect X2 dash here. So power factor would be 1, almost unity. That means under full load running condition, the power factor of the motor is high. When slip is high, then R2 dash by S is much less than X2 dash. So power factor would be R2 dash by S X2. So power factor is low. So that means starting power factor of the induction motor is low, and as the speed builds up or the slip goes down, the power factor increases. So full load power factor will always be higher than the no load power factor in case of induction motor. So if we plot power factors versus slip and current versus slip, so here let us take speed instead of slip. So when speed is 0, slip is 1, and when speed is synchronous, slip is 0. Here speed is synchronous. Okay. So at low values of slip, the power factor is unity, and for high values of slip, power factor is inversely proportional to S. So it is something like this. Okay, it will be like this. At low values of slip, it will be unity. At high values of slip, power factor decreases as slip increases. Okay, so as we move here, the power factor will reduce. What about the rotor current or the torque? In the high slip region, the rotor current will be V by under root R2 dash by S square plus X2 dash. So for high slip, what will happen? For high slip, what we can do is we can neglect R2 dash by S in comparison to X2. So I will be V by X2 dash, which is constant. For low slip, that is under running condition, I will be equal to R2 dash by S will be much higher than X2 dash, Vs by R2 dash. So current is proportional to slip under low slip condition. Okay, but under high slip, current is in constant. So it will be constant like this, and then it will reduce. Okay, this will be your rotor current. This is your power factor. So at high values of slip, it is constant, and for low values of slip, as the slip reduces, current also reduces. Here, as the slip increases, power factor reduces. It is inversely proportional to slip. So this will be the plot of current versus speed and power factor versus speed. So as the speed of induction motor is varied, the torque will vary, current will vary, as well as the power factor of the rotor will also vary. Now let us try to determine the maximum point in the characteristics, that is the maximum torque. It is also called as breakdown torque, or it is called as stalling torque. Okay, it is also called as pull out torque. So there are various names. You must recognize by any of these names that it is talking about the maximum torque in case of induction motor. Now the torque, the actual expression was given by 3 by omega Sm, then VE square under root RE plus R2 dash by S whole square XE plus X2 dash whole square into R2 dash by S. So to make the torque maximum, we have to make denominator minimum. And since we are talking about torque slip characteristics, so we have to vary the slip to maximize the torque. Denominator is given by this s will also come in the denominator. This will not be under root here. This will be directly term. Okay, so try to remember this. There should be no under root in the denominator, because what is the natural tendency is we will place the under root thinking that it is impedance, but it is impedance square. Okay, so this is the denominator. So we have to differentiate the denominator with respect to s and equate it to 0 to derive the maximum torque. Okay, so if we differentiate the denominator, then by product rule I am differentiating. First we will differentiate the first term. The differentiation will be 1 Re plus R2 dash by S whole square Xe plus X2 dash whole square, plus then we will differentiate the second term. The second term, this will be differentiated 2 times Re plus R2 dash by S, okay, into minus R2 dash by S square. Differentiation of second term will be 0. Now if we simplify this, it will be dd by ds. We will take common Re plus R2 dash by S plus 2s s times Xe plus X2 dash whole square minus R2 dash by S square. Minute. This dd by ds will be equal to, clear whatever I have written and restart here. dd by ds will be equal to Re plus R2 dash by S can be taken common from these two terms. It will be Re plus R2 dash by S, then minus 2 into R2 dash by S, because this S will get cancelled with this, plus Xe plus X2 dash whole square. Okay, so this will be 0. So this will become Re plus R2 dash by S. The other term will be Re minus R2 dash by S. Xe plus X2 dash whole square. So this will be Re square R2 dash square by S square plus Xe plus X2 dash whole square is equal to 0. So from here if we calculate S will be R2 dash divided by under root Re square plus Xe plus X2 dash whole square. This is the slip at which the maximum torque will occur. It can be written as SMT, slip for maximum torque. Now to determine the maximum torque, 3 by omega Sm Ve square Re plus R2 dash by SMT whole square Xe plus X2 dash square into R2 dash by SMT. This will be your maximum torque. So if we have to expand the expression, then we will bring the SMT into the denominator. RE square R2 dash by SMT square 2RE R2 dash by SMT XE plus X2 dash whole square. And here we will take SMT in the denominator. Here it will be R2 dash. 3 by omega SM VE square R2 dash, then SMT RE square plus XE plus X2 dash whole square, then it will be R2 dash by SMT plus 2RE R2 dash. Okay, so this will be the maximum torque. Now SMT is given by SMT is RE upon under root of this. So SMT, if we substitute, three by omega SM VE square R2 dash, then SMT is R2 dash by under root of this, R2 dash into under root RE square XE plus X2 dash whole square. R2 dash by SMT will give me under root RE square plus XE plus X2 dash whole square plus 2RE R2 dash. So this will be the expression for the maximum torque. Okay. So that is how we can derive the maximum torque using the SMT. So you have to remember the expression for SMT and then you can substitute it to determine the maximum torque. Okay. So now, suppose we again make an assumption that we neglect the stator impedance. Okay. If we neglect the stator impedance, that means RE will be equal to 0, XE will be equal to 0 and VE will be equal to V1. Then first of all, SMT, the slip for maximum torque will be R2 dash over under root 0 square 0 plus X2 dash whole square, that is R2 dash by X2 dash. So you have to remember this expression R2 dash by X2 dash. Then the maximum torque will be V1 square SMT R2 dash by SMT whole square plus X2 dash square. Here we will substitute SMT, that is R2 dash by X2 dash. So it will be maximum torque will be 3 by omega SM V1 square into R2 dash divided by R2 dash by X2 dash. So this will get cancelled out. Over this will be R2 dash divided by R2 dash by X2 dash. So this will also get cancelled out, plus X2 dash square. So how much will this come out? TEM will be 3 by omega SM into X2 dash square. It will be X2 dash over 2 times x2 dash square into v1 square. So it is 3 by omega sm v1 square by 2 x2 dash. So that is the maximum torque in case the stator impedance is neglected. Now we derived the torque using one expression, or there is one relation that relates air gap power and torque. Torque is equal to air gap power by omega s, which is constant. So air gap power is directly proportional to torque. So if torque is equal to TEM, air gap power will also be maximum PGM. Now air gap power is equal to I2 square into R2 dash by S. That is the power across R2 dash by S. So we can derive it using maximum power transfer. How we can do that? So let us draw the equivalent circuit. If we draw the equivalent circuit, refer to the stator side. Okay, this is R1, so RE, XE, X2 dash, R2 dash by S, VE. For maximum power transfer across R2 dash by S, this R2 dash by S must be equal to Z. Z is the impedance of this branch, which is equal to under root RE square plus J C plus X2 dash square. So from here SMT will be R2 dash by RE square plus XE plus X2 dash square under root. Okay, the same expression can be derived using the maximum power transfer theorem, because whenever the torque is maximum, the air gap power will also be maximum, because both are related by the synchronous speed. Okay, the air gap power is equal to synchronous speed into the electromagnetic torque developed. Now in case of wound rotor machine, what we do is we have a concept of external resistance, or we have a facility of adding an external resistance. But as we saw, maximum torque was 3 by omega s v1 square into 2x2. So it is not a function of R2 dash. That means by adding the external resistance, the maximum torque will remain same. Okay, so maximum torque does not change as we add the external resistance. But slip for maximum torque is R2 dash by X2 dash. So as we increase the rotor resistance by adding external resistance, the slip at which maximum torque will occur will increase, and the speed at which maximum torque occurs will decrease. As the slip increases, the speed will decrease. So as we increase R2, the curve is being shifted to the left. The slip for maximum torque is shifting to the left. That is, the slip is increasing or the speed is decreasing. What about starting torque? At starting, the slip is high, and we saw torque is inversely proportional to slip, and the torque was coming out to be how much in case of high slip? In case of high slip, we will say that R2 dash by S is much less than X2 dash. So the torque would come out to be starting torque 3 by omega s v1 square R2 dash by s times X2 dash square. So here the starting torque is proportional to R2 dash. So by increasing the rotor resistance, the starting torque will increase. So the curve is being shifted towards left, but the starting torque is increasing. Okay. So by adding the external resistance in the rotor of the wound rotor induction machine, the starting torque increases and the slip for maximum torque increases. That is, the speed at which maximum torque occurs is decreasing, but the magnitude of maximum torque is independent of the rotor resistance. Now one thing we can do is we can express any torque as a ratio of the maximum torque. Now any torque is given by 3 by omega Sm into V1 square. We are using the approximate expression R2 dash by S, R2 dash by S square plus X2 dash square. Now if it is divided by the maximum torque, 3 by omega Sm will get cancelled out because maximum torque is 3 by omega Sm V1 square by 2 X2 dash. So 3 by omega Sm will get cancelled out, V1 square will get cancelled out. It will be R2 dash by S into 2x2 dash divided by R2 dash by S whole square plus x2 dash square. Now how to simplify this? We have to write this in terms of SMT, or the slip for the maximum torque. So what we can do is we can divide it using x2 dash square. Divide both numerator and denominator by x2 dash square. So it will become R2 dash by x2 dash into 1 by S divided by, it will become R2 dash by x2 dash S whole square plus 1. So it will be SMT by S divided by SMT by S whole square plus 1. So if we divide numerator and denominator by SMT by S to make the numerator 1, here there will also be a 2 factor. So it will be 2 by SMT by S plus S by SMT. This is the ratio of any torque to the maximum torque. This is very important from gate perspective, as sometimes the maximum torque may be given to you and the slip may be given. We can determine any torque at any slip if we know the maximum torque and the slip for the maximum torque. So this expression you must remember at all times. Okay. So you must remember the case. How to determine the maximum torque? We have to determine the slip for maximum torque using the maximum power transfer. But you must always memorize the special case when the stator impedance is neglected. The slip for maximum torque is R2 dash by X2 dash. And the maximum torque is 3 by omega S V1 square by 2 X2 dash. These expressions are very necessary in which the stator impedance is neglected. Now let us consider the case when we are determining the maximum power, that is the maximum developed power, or PM. Now we know that R2 dash, this represents rotor copper loss. Okay, here Jx is Xc plus X2 dash. So here we will have air gap power minus copper loss. Here we will have mechanical developed power. So to maximize the mechanical power, we need to maximize the power across this resistance. That can be done using maximum power transfer theorem. R2 dash by 1 minus S by S should be equal to magnitude of impedance, which is under root R2 dash plus Re whole square plus X square. So it is R2 dash into 1 by S minus 1 under root R2 dash plus Re square plus X square. So this will come out to be R2 dash by S is equal to R2 dash plus under root R2 dash plus Re square plus X square. So the slip for maximum power, or the maximum developed mechanical power, that is SMP, will be R2 dash divided by R2 dash plus under root R2 dash plus Re square plus X square. This will be the slip for the maximum power. Okay. At this slip, the maximum power will be developed, across the mechanical terminals or at the shaft. Okay, because shaft power is mechanical power developed minus the rotational loss. So if mechanical developed power is maximum, so the shaft power will also be maximum. So remember, the condition for maximum power and maximum torque is different, because maximum power is the maximum power across the resistance R2 dash into 1 minus S by S, and maximum torque corresponds to air gap power, which is the power across R2 dash by S. So both cases are entirely different. So now if we plot power versus, or if we write down the slip for maximum power, it will be R2 dash over R2 dash plus under root R2 dash plus RE square plus XE plus X2 dash square. Whereas slip for maximum torque is simply R2 dash divided by under root RE square XE plus X2 dash square. Okay, these are the two different slips, slip for maximum power and maximum torque. Now if we draw the power slip characteristics at zero slip, okay, that is at slip is equal to 1, the thing is R2 dash into 1 minus S by S will be 0 when slip is 1. That means it is short circuited, so the power will be 0. So at slip is equal to 1, or at starting, the power is 0. At slip is equal to 0, the R2 dash 1 minus S by S will be infinite, that is open. So current is 0, power will be 0. Whenever it is short, that means voltage is 0. Then again the V into I power will be 0. If it is open, the V into I again will be 0, because I is 0. Okay. So between at n is equal to 0 and at n is equal to ns, at both cases power is 0. In between, the power passes through a maxima. And when slip is less than 0, that means it enters the generating region, so power is negative, because now machine is delivering power instead of absorbing the power. Even in braking region, the power will be negative, because the speed is slowing down, so it is returning the stored kinetic energy. Whatever is the kinetic energy stored in the rotor, it will return that energy. So it is indirectly operating as a generator, where instead of prime mover, the energy stored in the rotor is being used. Otherwise, prime mover delivers the mechanical power. Here mechanical power is stored in the device that is harnessed to produce the electrical power. So that is why power is negative. So remember, in generating as well as in braking region, power will be negative. In generating region, the machine is being rotated by prime mover, so it will deliver the electrical output. In braking region, whatever is the stored kinetic energy in the rotor acts as the prime mover and delivers the electrical output. So let us summarize what we have learnt in this lecture. We saw the at low slip, torque is directly proportional to slip. Okay. And at high slip, torque is inversely proportional to slip, but torque is directly proportional to rotor resistance. That is why at starting, high resistance is preferred, so that we have a high starting torque. Then we saw condition for maximum torque. The slip for maximum torque is R2 dash under root RE square plus XE plus X2 dash square. And then we derive the maximum torque after neglecting the stator impedance V1 square over R2 dash by S, sorry, V1 square by 2x2 dash. Okay, here SMT was R2 dash by x2 dash. Then we derived slip for maximum developed power. It was R2 dash over R2 dash plus under root RE plus R2 dash square XE plus X2 dash square. So that is what we covered in this lecture. So this is all about your torque slip characteristics of the induction motor. So whatever expressions we have covered, you must memorize those expressions, as this is the most important topic from this chapter.